with this particular problem, I have the mass number of two isotopes of boron, boron 10, boron 11, and I have the natural abundance. So I have the percentage that they are present in nature. I'm going to use that value to calculate the atomic weight. And we'll see how close we are to the periodic table value for the atomic weight. Now, you have an equation that you're going to need to use. It's number 3 of your question number 3 of your post-lab questions. They tell you that the atomic mass is equal to the relative abundance of isotope times the mass of the isotope. And you add them all together. Now, how do I get natural abundance into relative abundance? Well, all the relative abundance is the decimal form. So if I divide the natural abundance by 100, I put it back into a decimal. So that is the relative abundance. So my atomic mass, or excuse me, atomic weight will equal the relative abundance times the mass. Well, what's the mass of boron 10? What's the mass of boron 10? Because the mass number is protons and neutrons. So that mass number is 10. Put that in parentheses, make sure I calculate that first, and then I add boron 11 and its natural or relative abundance. So that's going to be 0.801 times 11. Now, just looking at those two numbers, what should my final answer be closer to, 11 or 10? 11, because 80% of this stuff is 11, right? So, when I fire this up and do my math, that gives me 1.99. That gives me 8.811. When I add them together, I get 10.8. And you don't know this yet, but that's labeled atomic mass units. Okay? And I rounded that to 3 sig figs. My exact number was 10.801. And as I look at the periodic table, I got the atomic weight is 10.811. So that was pretty close, wasn't it? Okay. Questions on that one? All right, here is the second one. I'll give you a second to write down this. Now, this one is a little bit tougher because I have to bring out some algebra knowledge and I have to bring out some knowledge of percentages. All right, I am trying to figure out the natural abundance through the relative abundance. Now, I have the atomic weight given to me. The atomic weight of lithium on the periodic table is 6.941. Now, we said before, and I'm just going to use abbreviations for this, that the relative abundance times the mass. Well, one lithium has a mass of 6. I add to that the relative abundance times 7. Now, I've got to set up some kind of an equation in which I can solve for the relative abundance, because obviously this is 1 relative abundance and this is 2, and they're not the same values, are they? If they are, it's extremely lucky that they are the same values. Okay? So, I have to determine percentages. And I know that whatever these two values are, they have to equal 100%, right? So, when I'm doing relative abundance instead of percentages, the relative abundance has to equal 1 for both of them. Correct? We're putting them into decimals. They have to equal 1. So, when I'm setting up my equation, I'm doing 6.941 is equal to x times 6. Let's not use that because that's going to get us a little confused. X times 6 plus, what's RA2 going to be? What's RA2 going to be? I don't want two variables, so I'm not going to make it y. I'm going to use some form of x. Well, if I know all of it is equal to 1, and I know this x, how about 1 minus x? And I know my brackets are bad. I should use brackets over parentheses or whatever. Maybe. Let me just get... That's not going to work. All right, it's not working, so I'm not doing it. I know my brackets are bad, my parentheses, deal with it, okay? Well, actually, I don't even want that one there. All right, this is going to really tick me off. Do I? Where? Do I have an undo button? I don't think so. It's a smart board. It's a lot smarter than me. How could I just erase before, though, and not now? Huh? Here? All right. Now we'll highlight it. All right. Anyway, let me redo it down at the bottom. So this is no good. 6.941 is equal to x times 6 plus brackets, then my parentheses, 1 minus x times 7. Then I close my bracket. Okay? So, what I'm doing now, and I'm going to run out of room here, is I'm going to work this equation. So, 6.941 is equal to 6x plus 7 minus 7x. Because I just distributed the numbers right there. So, what I'm going to do is I'm going to get my x's to one side, okay, which is going to be over here. So I am going to take, what's 6 minus 7? -1, but I don't want the -1, so that's why I'm going to bring it over here. Okay? So it's going to be 1x is equal to 7 minus 6.941. 1x equals 0.059. Okay? So, as I am looking at that, did you see how I did that? Okay? All I did, and I'm running out of room, okay? I'm running out of room. I had 6 minus 7 is -1, right? I took this 6.941 and I brought it over and subtracted it by 7. That's where I got the 0.059. All right, so I was just doing algebra to work my equation. I wish I had more room, but I didn't. So this is telling me that x is 5.9%. So what is 1 minus x? (94.1%), and that should equal 100. Now, you're going to need to be able to do this because you have problems like this on your post lab. Okay? Yeah, John? All right. The question is, why did I put 1 minus x right here? Correct? Well, if you remember up here, I said that these two things have to equal 100%. Okay? Now, if I have my relative abundance, 100% divided by 100 is 1. Okay? So, if I make this one x, right here, this one is x minus 1. Or excuse me, 1 minus x. Okay? Now, would this work if I had 3 variables? Or if I had 3 different isotopes? No, I couldn't do it. Since I only have 2, it'll work. If I would have 3 isotopes, I wouldn't be able to do it because there's too many numbers I don't know. All right? Does that help where the 1 minus x came from? Okay.